So thank you, everybody. I'm Cindy from McMaster University. Sorry, I forgot to list my university name here, so I have to acknowledge my university and the funding sources from ANSERC, as well as my collaborator from Singapore. So my talk today based on the interfacial area change and energy efficiency in organic solar cells. I will start with a scene paradigm of solar cells, followed by the challenges of organic solar cells. However, there's one missing parameter when we are discussing our Ball-Hill junction, that is interfacial areas. Then, in order to obtain the real interfacial area, we use DC bias AC impedance spectroscopy. And I will finish my presentation with the relationships between interfacial areas and energy efficiency. And as a promising new technology, organic solar cells have been a focal point in recent years. The energy efficiency has been improved to about 10% due largely to the synthesis of new chemicals. Despite the development, a considerable gap still exists when compared with silicon-based solar cells. One of the major reasons is the localized acetone and therefore the shorter acetone diffusion length. In polymer-based solar cells, the working volume of photoabsorption is therefore reduced. All this led to the introduction of Ball-Hill junction to increase the interfacial areas so that the acetones created will never be too away from the interface. So ideally, the Ball-Hill junction is three-dimensional interpenetrating bicontinuous network. However, the morphology is always or sometimes far from satisfactory. Previous studies on Ball-Hill junctions shows that the energy efficiency improvement has almost done by empirical try and error. For example, the different choice of solvent, control of drying and thermal annealing and vapor annealing in order to obtain two-phase separation with the optimal domain size about 10 nanometers. This slide shows our early work on morphology control by applying AC electric field during device fabrication. The sample with AC electric field shows the energy efficiency increased by 15%, and the IV characteristic curve have been shown that energy efficiency has been increased from 2.89 to 3.41. And when we are looking at the sample under AFM, we found that the sample with AC electric field shows a much smoother surface with much smaller domain size. The battle continued, and Aaron Higger found in 2011 that the diffusion bilayer devices can achieve the energy efficiency similar to that of Ball-Hill junction, and there's no significant difference between the morphologies of Ball-Hill junction and bilayer device. Does that mean the Ball-Hill junction device has a similar interfacial area with the bilayer device? Obviously, there's one missing parameter in organic solar cells, that is the interfacial area, which has blocked us from getting the whole picture of how far we are away from the optimal structure and how far we are away from the perfect energy efficiency. When we are looking at an example in fuel cells, by introducing the gas diffusion layer with the platinum nanoparticle of about 15 nanometers, the interfacial areas can be enlarged 600 to 1,000 times than the nominal area. However, when we are thinking about the electron pathways in organic solar cells, the ratio of interfacial area versus nominal area is still unknown. Therefore, the challenge becomes the measurement of the winding interface from a three-dimensional structure and by the measurement, we hope we can answer two more questions. The first is whether or not the Bohr junction has expanded the interface as expected. And the second, how does that affect energy efficiency? Usually, we use TEM or AFM to observe the interface. However, it's hard to get the real interface area due to the sample's nature, since we are looking at organic bicontinuous three-dimensional structure. So this is our approach to use capacitance measurement to obtain the values of the winding interface. Capacitance measurement was done by frequency scan under DC bias voltage, and the samples were put into a vacuum chamber, and the measurements were done directly after device fabrication without breaking the vacuum. That is because when we purposely admit a small amount of air into vacuum chamber to raise the vacuum pressure from 10 to the power of -9 to 10 to the power of -5, we found that the impedance data has changed a lot, and therefore vacuum seal is necessary, which has never been reported before. So on the left, the impedance data on one particular bias was plotted using Nyquist plot, which shows a semicircle along the real and imaginary part. It is typical for capacitor and resistor combination, and resistor R can be extracted from the real axis, and the capacitance C can be calculated from the top frequency. When the capacitance was plotted against the bias voltage, we obtain the capacitance versus bias voltage relationship. By the plot, we know that it follows a general pattern for a PN junction where the positive side is dominant by diffusion capacitance due to the voltage lagging behind the current, and the negative side dominant by the junction capacitance due largely to the space charge in the depletion zone. Since what we want to get is the interfacial area, so we are most focusing on the negative bias. Capacitance data under different structures with different materials were plotted at negative bias voltage. From the curve, we know that the PTB7 PCBM Bohr junction has the highest capacitance, followed by the P-switch-T PCB7 Bohr junction, then two annealed bilayer, followed by the non-annealed bilayer device of two different material systems. The data here allow us to track the interfacial area change. By lots of numerical calculations and IV characteristic curves, that is the final result. Here we have the ratio of interfacial area versus nominal area, and the y-axis is energy efficiency. There are lots of trends here. First, I want to point out that a real bilayer device is hard to obtain by solution process, and the data shows that the annealed bilayer showed about 2 to 4 times the interfacial area than the nominal area. And for the P-switch-T system, the energy gets saturated when the ratio is about 6 to 8 times the nominal area, which means when those loose domains are get connected, the excitome or the quantum of excitome has largely been reduced. And if we are try to increase the interfacial area ratio more, the energy efficiency won't be enlarged a lot. However, for PTB7 system, there's a linear trend found for energy efficiency. So more work on morphology is anticipated. And so far, the energy efficiency of Ball-Hill junction for PTB7 system is about 7.4%. So that is a short summary. So a comparison has been made between the energy efficiency versus junction area increase of organic solar cells. By comparing the interfacial areas of bilayer and Ball-Hill junction, we found that interfacial of latter was enlarged, matching a similar increase of energy efficiency from their bilayer counterparts. The method described here provides a possible way of measuring the interfacial area, which hopefully offer critical information in new structure assessment, leading to better understanding of device physics. And the method here may also be useful to other systems having bicontinuous structure where the interfacial area plays a key role. And this is my publication list, and thank you.